There are many elements that exist in the Earth's surface, in the atmosphere, in the Earth's crust, or anywhere else that you could possibly find them. Some have natural existence, some are synthetic, some occur in pure forms, some are found in mixtures and compounds, and thus require purification procedures to obtain them. You couldn't possibly exhaust all of them in studying, but there are some that we shall give special attention at the high school level due to their importance and abundance. Now they include carbon, sulfur, chlorine, and nitrogen. We shall look at the pure forms of these elements, and then we are going to look at their compounds. Carbon and some of its compounds. Carbon is an nonmetal falling under group 4 as an atomic number 6 and configuration of 2 to 4. It forms covalent bonds in most of its compounds. Carbon is found abundantly in living systems combined with hydrogen and oxygen. Carbon occur in pure forms as graphite and diamond, and in pure forms such as amorphous carbon and many other compounds. Allotropes of carbon. Now we said that allotropes are different forms of the same element in the same physical state. We also said that diamond and graphite are the two allotropes of carbon. Let us look at diamond. Diamond is colorless, transparent, and shiny. Now physically, that is how a diamond looks like. Structurally, in diamond, all the 4 valency electrons of carbon are used in the formation of the strong covalent bonds. Each carbon atom is thus bonded to 4 other carbon atoms, producing the hardest known substance. Now, because all the 4 electrons are used in the bonding, there are no delocalized electrons, and this is why diamond is a non-conductor of both heat and electricity. Diamond has a density of 3.51 grams per centimeter cubed and a high melting point of 3700 degrees Celsius because of the close packaging of the atoms and the strong covalent bonds. Because of the shiny appearance on polishing, diamond is used in making of jewelries. Because of the hardness, it is used in making of glass cutters and drill bits. Diamond is mined in South Africa, Tanzania, and some parts of India. The next allotrope of carbon is graphite, and graphite is a black, soft, and slippery crystalline solid. So that's the image of graphite. Structurally, in graphite, 3 of the 4 valence electrons of carbon are used in the formation of covalent bonds. There is thus free delocalized electrons in graphite, and thus it conducts electricity. Graphite structure constitutes of hexagonally arranged carbon atoms covalently bonded together, each atom to 3 others. The layers in graphite are held together by weak van der Waals forces. The layers thus slide past each other, and hence graphite is slippery in nature. It has a low density of 2.3 grams per centimeter due to the spaces between the layers. Graphite has a high boiling point of 4800 degrees Celsius and a melting point of 3500 degrees Celsius because of the strong covalent bonds. This makes it useful in making molds for casting metals. It is mixed with clay to make pencil lead because of the layers sliding past each other. Graphite is mined in South Africa, Sweden, Germany, and the United States. The last allotrope of carbon is fullerenes. These are synthetic carbon allotropes which occur in different shapes. The best known fullerene is carbon 60, shown here. As you can see, it is made up of hexagonally arranged carbon atoms. Let's look at what is called amorphous carbon, and these are impure forms of carbon and include charcoal, coke, and coal. They contain small amount of graphite. Some, like charcoal, can absorb gases and liquids, making it useful for gas masks. It is also used in absorbing impurities in sugar refining industries. When mixed with rubber, carbon black is used in the manufacture of tires. Let's now turn and look at chemical characteristics of carbon, and we shall start with combustion in air. When carbon is heated, it glows red. A colorless gas is produced which forms a white precipitate when bubbled through lime water. This gas is definitely carbon dioxide. All forms of carbon burn in oxygen to form carbon dioxide, although at different temperatures. The red glow indicates that the reaction produces heat. It is exothermic. Reduction properties of carbon. When a mixture of copper 2 oxide and carbon are heated, the black mixture turns into a brown metal and a colorless gas is produced. So the black copper 2 oxide there is mixed with the black carbon. So a colorless gas is produced that forms white precipitate when bubbled through calcium hydroxide, which means the gas is carbon dioxide. The brown solid there. So the brown solid is copper metal and the gas is carbon dioxide. Carbon reduces copper 2 oxide to copper and itself is oxidized to carbon dioxide according to this equation. Equally, carbon removes combined oxygen from zinc, lead, and iron according to these equations. However, it cannot reduce the oxides of potassium, sodium, magnesium, calcium, and aluminium. This reducing property is used in the extraction of metals from their ores. At very high temperatures, about 1200 degrees Celsius, carbon reduces steam to hydrogen and itself is oxidized to carbon monoxide or carbon 2 oxide. The mixture of the two gases is called water gas according to this equation. Reaction with concentrated nitric acid and sulfuric acid. When a small amount of carbon is added to warm nitric acid, a brown gas is produced. Another colorless gas that forms white precipitate on lime water is also produced. The brown gas is nitrogen dioxide and the colorless one is carbon dioxide according to this equation. If sulfuric acid is used, sulfur dioxide is liberated in place of nitrogen dioxide according to this equation. The concentrated acids react with carbon because they are strong oxidizing agents. Notice that the state symbols for concentrated acids is liquid and not aqueous. Let's look at the first compound of carbon, and that is carbon 4 oxide. Carbon 4 oxide is a molecular substance and the most stable oxide of carbon. It has a 0.03 atmospheric abundance. This concentration varies with high concentration seen in cities and industrial areas. The concentration is, however, low in forested areas. In the laboratory, carbon 4 oxide is prepared by the action of dilute hydrochloric acid on calcium carbonate. The gas is passed through sodium hydrogen carbonate or water to remove traces of hydrochloric acid fumes in the gas. If you need it dry, the gas can be passed through sulfuric acid or use anhydrous calcium 2 chloride. Any other carbonate may be used with a suitable acid. Dilute sulfuric acid should, however, not be used with the carbonates of lead, barium, and calcium. Why? Because the sulfates of these metals are insoluble and they form a coat preventing further reactions. For the same reason, lead 2 carbonate should not be used with hydrochloric acid because lead 2 chloride formed is insoluble. Properties of carbon 4 oxide. Carbon 4 oxide is a colorless and odorless gas. It is denser than air, and that is why it is collected by downward delivery. It neither burns nor does it support combustion. Carbon 4 oxide is slightly soluble in water, forming an acidic solution of carbonic acid. It reacts with sodium hydroxide, forming sodium carbonate according to this equation. Now, in excess, a further reaction occurs leading to formation of sodium hydrogen carbonate. When briefly bubbled through calcium hydroxide, also known as lime water, a white precipitate is formed, and this is the insoluble calcium carbonate. This is the confirmatory test for carbon 4 oxide. When bubbled for a while, the white precipitate dissolves due to formation of soluble calcium hydrogen carbonate. A burning magnesium continues to burn in carbon 4 oxide, producing a white solid of magnesium oxide and black specks of carbon. The burning produces a lot of heat that decomposes carbon 4 oxide into carbon and oxygen according to this equation. The other oxide of carbon is carbon 2 oxide, also called carbon monoxide. Now, this is an oxide of carbon in which the carbon atom forms 3 covalent bonds with 1 oxygen atom. Carbon 2 oxide is a molecular substance. However, one of the shared electrons pair is donated by the oxygen atom alone. It forms a dative covalent bond that we call coordinate bond in the previous chapters. In the laboratory, carbon 2 oxide is prepared by the dehydration of methanoic acid using concentrated sulfuric acid. Ethindioic acid, also known as oxalic acid, may also be used in place of methanoic acid. The gas so produced should be passed through concentrated solution of sodium hydroxide to remove the carbon 4 oxide. We can also prepare the gas by passing carbon 2 oxide over heated charcoal. Physical properties of carbon 2 oxide. Carbon 2 oxide is slightly less dense than air, and due to the closeness in density, it cannot be collected by downward delivery. It is colorless and odorless, slightly soluble in water, forming a neutral solution. Carbon 2 oxide is extremely poisonous. Once inhaled, it combines with hemoglobin in the blood to form carboxyhemoglobin, therefore preventing the formation of oxyhemoglobin and leading to suffocation. This is why carbon 2 oxide is commonly referred to as a silent killer. Carbon burns in air with a blue flame to form carbon 4 oxide. It also readily removes combined oxygen from metal oxides such as lead, copper, and iron. In turn, it is oxidized to carbon 4 oxide according to these equations. The other compounds of carbon are carbonates and hydrogen carbonates. Carbonates are salts of metal or ammonium ions with carbonate ions. They occur naturally in rocks such as limestone. Hydrogen carbonates are salts derived from carbonic acid formed by partial displacement of the hydrogen by a metal or ammonium radical. Hydrogen carbonates of sodium, potassium, and ammonium are solid at room temperature. Those of calcium and magnesium exist in solution only, while those of other metals do not exist at all. Effects of heat on carbonates and hydrogen carbonates. We also saw when we tackled the topic on salts that all carbonates, with the exception of those of sodium and potassium, are decomposed by heat into metal oxides and carbon 4 oxide according to these equations. The ammonium carbonate decomposes to produce ammonia, carbon dioxide, and water. On the other hand, hydrogen carbonates of sodium and potassium decompose into carbonates, carbon 4 oxide, and water according to these equations. Now, there is a group of compounds of carbon which have a great commercial value, and that is sodium carbonate and sodium hydrogen carbonate. We take a case study on the large production of this. Sodium carbonate is a raw material in the glass and paper industries as well as useful in water treatment. It is extracted from either the two processes, that is from trona, or by what is called the Solvay process. Let's look at extraction from trona. Trona is a double salt containing both sodium carbonate and sodium hydrogen carbonate plus water of crystallization. Trona occurs in lakes with inlets but no outlets. In Kenya, trona is mined at Lake Magadi. As trona is mined from the lake by dredgers, it is transported to the factory. Here it is put through a washery where it is washed to remove mud and small rocks. Now the product then moves to the next stage where it is centrifuged to remove water and further purify it. The product is dry trona. The dry trona is then heated to about 300 degrees Celsius in a kiln to decompose sodium hydrogen carbonate according to these equations. Finally, the sodium carbonate is ground, sieved, and packaged ready for market. Now this process can be shown here by the flow chart. So there you have the trona from the lake is taken into the washery where water is added. What comes out is a mixture of trona and water, and this mixture is taken to a centrifuge. It undergoes centrifugation. So in centrifugation, water is removed and what comes out is dry trona. Dry trona is taken into a kiln, which is usually a cylinder that rotates as heating goes on. Now the kiln heats the dry trona to 300 degrees Celsius. So the sodium hydrogen carbonate decomposes and what comes out is sodium carbonate. The sodium carbonate is taken to a heat exchanger where it is cooled. Now once it is cool, the sodium carbonate is taken to a grinder where it is ground into powder, it is sieved, and then finally it is packaged and stored ready for market. The other source of sodium carbonate and sodium hydrogen carbonate is in the Solvay process. Now in this process, sodium carbonate and sodium hydrogen carbonate are manufactured from simple raw materials. Now let's look at this process of Solvay. Let's look at the Solvay process. The Solvay process is a complex one involving a series of reactions and processes, but also very economical and very reasonable in energy use. So the process has several towers. We have tower 1, also called the Solvay tower. There's also tower 2. Tower 3, also called the carbonator. In tower 4, it's a roaster where heating takes place. We also have a filter, roaster again there, and we also have the source of ammonia. Now the process starts by dissolving ammonia in brine in the Solvay tower number 1. Now here a lot of heat is produced in the process, which is controlled by regulating the flow of brine in the Solvay tower. Now what is formed there is what is called ammoniacal brine. The ammoniacal brine produced is then pumped into the carbonator tower 3. Notice that we move from tower 1 to tower 3. The ammoniacal brine trickles from the top. Meanwhile, in chamber 4, coke and limestone are heated to produce carbon 4 oxide and calcium oxide. The carbon 2 oxide produced in that roaster is then pumped to the carbonator from the bottom. Now the reactions in the carbonator are shown here. Ammonia combines with carbon 4 oxide and water to form ammonium hydrogen carbonate. This ammonium hydrogen carbonate reacts with sodium chloride to form ammonium chloride and sodium hydrogen carbonate. The carbonator is constantly cooled to reduce the heat generated. The sum of the reaction in the carbonator can be thought of as follows: ammonia plus carbon 4 oxide plus sodium chloride plus water forms ammonium chloride and sodium hydrogen carbonate. The sodium hydrogen carbonate and ammonium chloride are separated by filtration. Ammonium chloride is taken back into chamber 2. Sodium hydrogen carbonate is heated to dry and also decompose at 300 degrees Celsius to sodium carbonate. The carbon 4 oxide and water are then recycled in the process. Sodium carbonate is now ready for packaging. The initial carbon 4 oxide is obtained by decomposition of calcium carbonate, that is limestone, in chamber 4. Afterwards, the process is self-sustaining in as far as carbon 4 oxide is concerned. The ammonia used is obtained from the Haber process, and the calcium oxide produced in the kiln, that is chamber 4, is slaked with water and then mixed with filtrate ammonium chloride to produce ammonia gas, water and calcium chloride according to these equations. Now, a closer look at this process shows an efficient system with minimal wastage and effective pollution control. Carbon 4 oxide and ammonia produced are recycled to minimize cost and eliminate pollution. Water produced is also recycled. The coke burned in the kiln produces the necessary heat needed by the process and hence no large consumption of energy. The process should actually be situated near a river to have enough water for cooling purposes. Now here is a summary of the reactions that take place in different chambers. Now, the raw materials for the Solvay process are sodium chloride, calcium carbonate, coke, and ammonia, and these materials are cheap and readily available. We've said the process is very efficient, with the only waste being calcium chloride. All other materials are recycled.
You can make a bigger difference in the world. You can make a positive change in your career. You can make a greater contribution to the greater good. And you can start today by earning your degree online at Walden University, where advanced degrees advance the quality of life.